Okay, this is the start of the benzene topic, and you've probably seen benzene, which is usually can be written like this. So it's 6 carbons in a ring with alternating single and double bonds, and sometimes it is written like that with a circle, and for reasons which we'll see why in a bit. For this start video, though, I just want to explain some background, and they won't ask you about this background in exam questions, but it's important. It makes it a lot easier to understand what's going on, I think, if you do know this, which is going a bit beyond A-level confines of the specification, but it will help us. Right, if we think about carbon, we have got carbon is 1s2, 2s2, 2p2. So the 1s electrons are not involved in bonding, but here we've got 2s, and you've got 1 electron, 2px and 2py. Well, to summarize, what happens is these orbitals, they mix. They don't stay like that. They mix, or the proper word for it is they hybridize. Hybridize, okay. And these are actually called sp3 hybrids. You don't need to know that, but you may, if you're looking, researching, you'll see that written down. So it's a mixture of the s and the p orbitals, and so there's the carbon atom in the middle, and you get 4 orbitals, and they are they're arranged in that characteristic tetrahedral shape. So in methane, for example, the electrons do form these sp3 hybrids, okay, and you get the characteristic shape of methane, the tetrahedron. Okay, now what can happen is, if you look at this situation down here, we don't have sp3 hybrids. We have 3 times sp2 hybrids, which are shown in red, and you have 1 p orbital, which is unhybridized. And that, as I've shown in blue. Now this happens whenever carbon forms a double bond. So let's have a think about ethene, for example. If you've got ethene, and we should be fairly familiar with the shape of ethene, so I'm going to draw it. We know it's a flat structure. So carbon's here, right? So we have these the hybridized orbitals here, which I've drawn in red, and they're forming the sigma bonds. Each carbon's got 3 of those, you can see. They form the sigma bonds to the hydrogens. And also what we've got here, on each carbon, you have got those p orbitals, which are unhybridized in blue. They're the p orbitals. And you should probably see what's coming here is that those 2 p orbitals, they overlap to form the pi bond. So the pi bond is formed between the 2 unhybridized p orbitals. Okay, so that you can probably see where this is going, because you can see benzene there, which I've drawn up there. Oh, I've crossed it out now. Benzene has got a lot of double bonds in it, so we're going to be concerned with these unhybridized p orbitals a lot and how they overlap. Okay, now before we start off with benzene, let's have a think about this compound, which is, let's think about, if I drew it skeletally, it would be, sorry, if I drew it skeletally, it would be like that, which is butadiene. Okay, so it's got, it's got its alternate. It's got 2 double bonds there. Now we think about what's going on here. Here's 1 unhybridized p electron, Another one there on that one. Okay, so you might think, well, what is happening with this then is, you might think it forms 2 pi bonds. And one there like that. Now, that is not what happens, is because if you think, look at the distance between those 2 p orbitals is the same as the distance between those 2 p orbitals and those there. So instead of just mixing like that, the whole lot all mixed together. So what happens is you get this. So you have your carbons there, all sigma bonded, and you'd end up with one with the electrons. Okay. So instead of forming these 2 discrete pi bonds, you get a sort of area of high electron density above the molecule and below. That's what happens. Now, this is more stable. Why is it more stable? Well, because the electrons are not shoved into a small space. Here they're shoved into 2 little small spaces. Here they can spread out more. They can use this bit here, yeah? And so that makes it's a lower energy configuration. So you've got here, which will say we've got the electrons are delocalized. And this can happen whenever you have a pattern of alternate double and single bonds. So if we had, for example, let's draw another one. So a double bond there, and this one here, so this is penta 1,4-diene. There's no electron, no delocalization there. Because if you think about it, let's draw our carbons. And you can have unhybridized p electrons here, 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 and here. Well, they can't jump across this gap here, it's too big. Okay, that gap is a 2 bond length, it's not a 1 bond length, so you don't get no electron delocalization there. Right, which brings us on to benzene, which I'll cover in the next video. But benzene, we can see it is drawn like this. That has alternate single and double bonds. And so what happens there, you get electron delocalization, which occurs over the whole of the thing. So that's why benzene we often draw like that to show that that's what's happening. And it is a lot more stable than you would expect it to be. That means it's less reactive than you'd expect it to be. And that's what we're going to talk about in the next video. But for the time being, just get this idea. Whenever you have alternate double single bonds, you have stabilization and you get electron delocalization.